There is a security risk from dirty high-order bits in Solidity. Recall that the EVM word size is 256 bits or 32 bytes. And there are multiple types in Solidity whose size is less than 32 bytes. Using variables of such types may result in their higher order bits containing dirty values. And what this means is that they may contain values from previous writes to those bits that have not been cleared or zeroed out. Such dirty outer bits are not a concern for variable operations because the compiler is aware of these dirty bits and takes care to make sure that they do not affect the values of variables. But if those variables end up getting used or passed around as message data, then that may result in them having the different values and causing malleability or non-uniqueness. This is a risk that needs to be kept in mind when looking at contracts that have variables of such types. There is a security pitfall related to the use of incorrect shifts in Solidity assembly specifically. Solidity assembly supports 3 different shift operations: shift left, shift right, and shift arithmetic right, all of which take 2 operands x and y. And these operations shift the y operand by x bits and not the other way around. This can be confusing, understandably, and the developer may have used these 2 operands interchangeably, in which case the shift operation does something completely different from what the developer anticipated. So this is something that needs to be checked when looking at shift operations in Solidity assembly. The use of assembly in Solidity itself is considered as a security risk because assembly bypasses multiple security checks such as type safety that is enforced by Solidity, and developers end up using Solidity assembly to make the operations more optimized and efficient from a gas perspective. But on the flip side, this is very error prone because the assembly language EUL is very different from Solidity itself and requires much greater understanding of the syntax and the semantics of that assembly language. So the use of Solidity assembly not only affects readability and maintainability and also the auditability because the auditors themselves might not be aware of the EUL language, the syntax and semantics. So all these aspects result in the recommended best practice of trying to avoid Solidity assembly as much as possible, or if absolutely required, then the developers and the security review should double check to make sure that they've been used appropriately in the context of the smart contracts. There is a security pitfall that arises because of the use of the Unicode right to left override control character in Solidity smart contracts. This causes the text to be rendered from right to left instead of the usual left to right. And this reverse rendering confuses the users as well as the security reviewers from understanding what the real intent is of that particular snippet of the smart contract. So the best practice here is to ensure that such confusing Unicode characters, the RTLO control character, is not used within smart contracts at all. There is a best practice related to the use of the constant specifier for state variables in Solidity. State variables whose values do not need to change for the duration of the lifetime of the contract can be declared as constant. This saves gas because the compiler replaces all the occurrences of such state variables with the constant value. And this effectively means that reading such state variables no longer requires the expensive sload instructions. So the best practice is to identify such state variables whose values do not need to change over the lifetime of the contract and declare them as constant. This saves gas, but it also has an additional side effect on improving security because such state variables can no longer be accidentally changed within the different functions of the contract. There's a security best practice related to variable names. This ties to the programming style guidelines that we discussed in the Solidity module. And in this context, the names of variables should be as distinct and unique from each other as possible. Because if they are very similar, if they differ by only a few characters or one character, then it could be confusing both to the developer as well as to the security reviewer. And from a developer's perspective, it could lead to replaced usages where the developer uses a different variable than what was intended. And this, as you can imagine, can have disastrous effects to the functioning of the smart contract. So variable naming affects readability, it affects the maintainability of the code, and also affects the auditability of the code. And the best practice is to use very distinct names for the variables, meaningful names for the variables, so that errors are avoided. Another security pitfall related to variables is the use of uninitialized state or local variables. Recall that in Solidity, the default values of uninitialized variables is 0. This results in address variables ending up as 0 addresses and Boolean variables taking the value of false because 0 is effectively false. We have talked about the risks from 0 addresses. Booleans being false by default will result in the conditionals taking a different branch than what was intended. The best practice here is to make sure that state and local variables are initialized with reasonable values so that errors are avoided from having their default values being used. There is a security pitfall related to the use of uninitialized storage pointers. Local storage variables that are uninitialized can point to unexpected storage locations within the contract. This, as you can imagine, can lead to developers unintentionally modifying the contract state, which can lead to serious vulnerabilities. Given that this is so error prone, Solidity Compiler 0.5.0 started disallowing such pointers. There was a security risk in using uninitialized function pointers within constructors of contracts. This was because of a compiler bug that resulted in such usage causing unexpected behavior. This compiler bug was present in the versions shown and has since been fixed. There is a security risk in the use of long number literals within Solidity contracts. These number literals may require many digits to represent their high values as constants or many decimal digits of precision, which, as you can imagine, is error prone. So for example, if one were to define a variable representing ether, then it would need to be assigned a number literal that has 18 zeros to represent the 18 decimals of precision. So the developer may accidentally use an extra zero or miss a zero, in which case the ether precision is different and the logic using this variable will be broken. The best practice here is to use the ether or time suffixes supported by Solidity as applicable, or to use the scientific notation which is also supported by Solidity. Older versions of Solidity produced unexpected behavior with out-of-range enums. What this meant was that if, for example, we had an enum E with a single member A as shown here, then E of 1 is out of range. This is because recall that indexing of enum members begins with 0. So E of 1 here is out of range because there's a single member. And this out of range enum produced unexpected behavior in Solidity versions less than 0.4.5. This was due to a compiler bug which has since been fixed, and the best practice until the fix was applied was to check the enums, the use of enums, to make sure they're not out of range. This best practice is related to the use of public functions in smart contracts. Recall that Solidity has the notion of visibility for functions. There are 4 visibility specifiers: internal, private, public, and external. This particular best practice is related to the use of the public visibility versus external visibility. Public functions consume more gas than external functions. The reason for this is because the arguments of public functions need to be copied from the call data component of EVM to the memory component. And this copying produces more bytecode for such public functions, which therefore consumes more gas. And this copying is not required for external functions where their arguments can be left behind in the call data component of EVM. So this is the key difference that leads to public functions consuming more gas than external functions in Solidity. So if there are functions in the contract that are never called from within the contracts themselves, then such functions should be declared as external visibility and not public visibility. And this leads to better gas efficiency. Let's now talk about the security risk from dead code. Dead code is any contract code that is unused from the contract's perspective or even unreachable from a control flow perspective. And this could be indicative of programmer error or missing logic that leads to the developer adding this code to the contract but not adding the logic that actually makes use of this code. This is certainly an opportunity for optimization because dead code increases the code size of the contract that during deployment leads to increased gas costs. However, this also impacts readability of the code, maintainability of the code, and auditability of the code, all of which affect security indirectly. Let's consider 3 scenarios in which dead code affects the security of smart contracts. The first scenario is where there is code in the contract that is in fact dead, but the developer or the smart contract auditor does not realize that this is dead code. If such code implements security checks, then we may assume that those checks are being enforced and improving the security, but in fact they are not effective because they are in dead code. So they reduce the security of the smart contracts effectively. The second scenario is where there is dead code in the smart contract and the developers are aware that this code is dead but decide to leave it in the contract without removing it. In such cases, such code may not be tested because the developers know that this is dead code, and because of this they may end up with security vulnerabilities contained in them, or they may contribute to such vulnerabilities. And later on, if someone else decides to use this dead code, at that point, because it is untested, the vulnerabilities contained in them or affected by them get manifested in the contract and affects the security negatively. The third scenario is that of mistaken identity, where there is code that is actually used within the smart contracts, but the developers incorrectly determine that this is dead code and remove it. In such scenarios, if that code implemented security checks or actually improved security because of their logic, then removing it reduces the security of the code. So effectively, dead code contributes to the security of smart contracts indirectly in potentially significant ways. So the best practice is for the developers to determine if a particular piece of code is used or dead, and if it is dead, determine if it actually needs to be used, and if not, remove it from the contracts. And if it needs to be used, then add logic that uses that code in the correct manner. There are security risks associated with function return values in Solidity. Recall that In Solidity, functions may take arguments, implement logic that uses those arguments along with some local and global state, create some side effects because of all that logic, and then may return values that reflect the impact of that logic. Now, for functions that return such values, the call sites are expected to look at those values and use them in some fashion. And the reason for this is because those return values could reflect some error codes that are indicative of some issues that happened during the processing within that function, or they could reflect the data that is produced as a side effect of that execution of the logic within that function. But if these return values are not used at the call sites, then that could be indicative of some missed error checking that needs to happen at the call sites, or in cases where there was data that was being returned without any errors, not using that data at the call sites could result in unexpected behavior. In both these scenarios, these could affect the security of the contract if that error checking or the missing logic due to not using that data returned affected the security aspects of the smart contract logic. So the best practice here is to see if a function needs to return values, and if functions are returning values, then all their call sites should be checking those return values and using them in appropriate ways. And if those call sites, any of those call sites are not using the return values and it does not affect the security, then the developers or the auditors need to evaluate if the functions need to return any value at all and remove the values from being returned from those functions. Another aspect that needs to be paid attention to is the use of variables in contracts. These could be state variables or local variables. And the specific aspect is if these variables are declared but are never used within the contract. This could be indicative of missing logic that is expected to be there and using these variables in certain ways but is missing because the developer forgot to add it. Or it could simply be indicative of some optimization opportunity where such variables can actually be removed and reduce the size of the bytecode and therefore reduce the amount of gas that is used either during deployment or during runtime. So the best practice here is to pay attention to all the variables that are declared in functions or in the contract as state variables, see if they're used, and if they're never used, then determine if they need to be removed for optimization or if there is any logic that is missing that needs to be added that uses those variables. There are potential security risks from function statements that are redundant. Redundant statements are statements that either have no side effects or that do have side effects but are made redundant because there is other code, other statements that have the same side effect. In either scenario, these are indicative of programmer error or missing logic that needs to exist to make these statements not redundant. Or they may just present an opportunity for optimization where these redundant statements need to be removed, reduce the size of the contract, and therefore make it more gas efficient for the contract to be deployed or execute at runtime. So the best practice here is to evaluate if statements are redundant, and if so, determine if they should indeed be having any side effects and add such side effects, or if they are indeed redundant and do not affect the security in any way, then remove them. So the impact of such redundant statements could be indirect to security because of the errors and the logic that we talked about, or they could be direct where such redundant statements are actually meant to enforce certain security checks, and because they're redundant, those checks never get executed and directly impact the security of the contract in a negative way. Let's now discuss a set of security risks that manifested themselves because of compiler bugs. These were bugs in older versions of the Solidity compiler that have been since fixed. They are very specific to certain data structures, certain complex data structures, or very specific conditions that one may not often encounter in smart contracts typically seen. And because of that aspect, we will not be able to get into the details of these compiler bugs and their security risks. So I would encourage you to take a look at the documentation from the Solidity team that goes into the details of some of these bugs. But nevertheless, taking a look at the higher level aspects of these compiler bugs would hopefully let us appreciate the complexity of some of these compiler bugs and the security risks that they may pose. This specific compiler bug was related to storage arrays and signed integers. And their usage was enabled by the ABI encoder v2, which was a pragma directive that needed to be explicitly specified until the latest versions, but in the latest version is used by default. So this specific bug arose when assigning an array of signed integers to a storage array of a different type. And under such assignments, it led to data corruption in that array. And this bug was present in the versions shown, which are much older versions than the latest one that we often encounter. So it's very unlikely that we'll look at smart contracts using these much older versions, but something to be kept in mind. This is another compiler bug related to constructor arguments. A contracts constructor that takes structs or arrays that contain dynamically sized arrays made possible because of ABI encoder v2 reverted or decoded to invalid data because of a compiler bug that was present in the versions shown. There was a compiler bug related to storage arrays in Solidity, specifically those with multi-slot elements, again made possible because of ABI encoder v2. Such storage arrays containing structs or other statically sized arrays were not read properly when they were directly encoded in external function calls or using the ABI encode primitive. And this bug was present in the versions shown here. Another compiler bug was related to the structs type, specifically the call data structs. Reading from call data structs that contained dynamically encoded but statically sized members could result in incorrect values being read. And this again was limited to the compiler versions shown here.